Welcome to The Explainer. Today, we are diving headfirst into the world of geometry, specifically Chapter 17, to get a handle on circles. We're going to break down the core rules that make chords and arcs tick, and you'll see how even the trickiest-looking problems can become pretty straightforward. Okay, so here's the game plan. First, we'll get the basic language down, then I'll show you two really powerful properties. We'll even see how one of them works with a classic theorem you already know. After that, we'll use these ideas to solve a proof, and then we'll wrap it all up with your brand new Circle Superpowers.
All right, first things first, decoding chords and arcs. You got to know the key players before you can understand the game, right? These are the absolute fundamentals for everything that comes next.
So what's a chord? It's really simple. It's just any straight line that you draw from one edge of a circle to another. That's it. It doesn't matter where the points are as long as the line connects them.
Now the diameter, well, think of it as the VIP of chords. It's special because it has to pass right through the dead center of the circle. And because it does that, it's also the longest chord you can possibly make. So just remember, every diameter is a chord, but not every chord gets to be a diameter. Okay, on to our first big trick. I call this the perpendicular power move. This is one of those fundamental rules that once you know it, gives you this incredible shortcut for solving problems. It's a total game changer, for sure.
Okay, I know, it sounds a little textbooky, but this is the rule you absolutely have to burn into your brain. It's called a power move for a reason, and what it actually does is beautifully simple. So check this out. You take any chord, you draw a line straight from the center of the circle down to it, and you make sure it hits at a perfect 90-degree angle. When you do that, it always, and I mean every single time, splits that chord into two perfectly equal halves. This little fact is the key that unlocks so much. And that brings us to Section 3, Pythagoras to the rescue. Now we get to see how our new power move teams up with an old friend, a theorem I know you've seen before, to find all sorts of missing lengths. So let's look at a classic problem. You've got a circle, you know the radius is 25 centimeters, and you've got a chord that's 48 centimeters long. The puzzle is, how far is that chord from the center? First, let's just lay out what we know. The radius is 25. The chord is 48. But wait, because of our perpendicular power move, we know that the line from the center to the chord cuts it in half. So half the chord is 24. And just like that, look what we've made. A beautiful little right-angled triangle with the radius as the hypotenuse. And once you see that triangle, you know what to do, right? We just plug the numbers into the Pythagorean theorem. So 25 squared equals our mystery distance squared plus 24 squared. That gives us 625 equals distance squared plus 576. A quick little rearrange and we find that the distance squared is 49. You take the square root of 49, and there it is. The distance from the center of the circle to the chord is exactly 7 centimeters. See that? Our little power move rule just made that whole problem completely solvable. Pretty cool, huh? Now for our second major property. This one is all about relationships. It's a powerful connection between three different parts of a circle: the angles at the center, the curved arcs on the edge, and the straight chords that connect them. Think of this as a geometric 3-for-1 deal. It's awesome. If you've got two angles at the center of a circle and you know they're equal, well then you automatically know that their matching arcs and their matching chords are also equal. They're all congruent, which is just the fancy geometry way of saying they're the exact same size. And don't forget, this is totally a two-way street. If you start out knowing that two chords are the same length, you can instantly say, well then their arcs and their central angles have to be equal too. It doesn't matter which piece of the puzzle you start with, the connection always holds. All right, time to put this new rule to work. In Section 5, we're going to see how this congruence connection lets us slice through a proof problem like it's nothing. So here's our mission. We need to prove that arc AB is the same size as arc CD. Now, based on the rule we just learned, the easiest way to do that is to first figure out the size of their central angles, angle AOB and angle COD. If they're the same, we're golden. Okay, we know a straight line, like our diameter, is always 180 degrees. So all those angles on one side have to add up to 180. That means for each of our mystery angles, we just need to calculate 180 minus 100 minus 35. And what do we get? We get 45 degrees for both of them.
And there it is, clear as day. This chart just spells it out for us. Angle AOB is 45 degrees and angle COD is 45 degrees. They are perfectly equal. This is the piece of evidence we were looking for.
And because those two central angles are equal, our congruence connection rule just kicks right in. Boom! If the angles are the same, then the arcs have to be the same. So we've officially proven that arc AB is congruent to arc CD. Proof complete. So, let's do a quick recap of the two awesome geometric superpowers you've just added to your toolkit. These are the things you'll use over and over again when you're dealing with circles. These are the two big ones, right here. The first rule, our perpendicular power move, is your secret weapon for finding lengths. And the second, the congruence connection, lets you prove that different parts of a circle are equal. If you master these two ideas, you've pretty much cracked the code for basic circle geometry. So now you have these tools. You see how just a couple of simple rules can totally unlock the hidden logic of circles. This isn't just about passing a test. It's about learning to see the elegant patterns in the shapes all around us. So the real question is, now that you know these rules, what other secrets do you think a circle is hiding?